All right, Chapter 7, Section 1. We're going to look at the uniform probability distribution. We'll talk about what that means and what it looks like. We'll look at normal curves, um, and then we'll look at the properties of a normal curve, and then we'll explain the role of area in the normal density function. Okay, so we're really going to be looking at setting up the basis, the foundation for normal distribution, right? Bell-shaped curve. So we'll get back into the empirical rule and all of that that we have kind of looked at in previous chapters, but not um, to the extent we will here. So just to kind of illustrate a uniform distribution, I pulled in this example, which is pretty cool. The post office is supposed to deliver a package to the front door, and the arrival time is somewhere between 10 a.m. and 11, right? So let variable X represents the time from 10 and the delivery is supposed to take place, right? Which would be 11. So X equals 0 is 10, X equals 60 is 11, right? 60 minutes. Well, and you split it up with all 1 minute intervals in between 0 and 60. If it's going to be delivered between 10 and 11, then it could show up at 10:15, could show up at 10:20, 10:30, 10:40, whatever, 10:55 if you want to. And that would suffice a delivery between 10 and 11, right? So all 60 minutes of that particular hour all have the equal probability of them showing up for delivery. There's not one weighted more than the other. Okay, does that make sense? We only get mad if they do not deliver it by 11, right? So anything between 10 and 11, we're like, all right. So because the two intervals of length are between 0 and 60 inclusive, all are likely, and the random variable is said to have a uniform probability distribution. So what does that really look like? Well, before we do that, we got to make sure we understand the probability density function is an equation that's used to compute probabilities of continuous random variables, right? It must satisfy the following two properties: the total area under the graph of the equation, overall possible values of the random variable must equal 1, right? So for 60 minutes, for it to be delivered at 10:01 is 1/60th, right? So every minute's a 1/60th. So if you do that, add those up, it would be 60 over 60, which equals 1. The height of the graph of the equation must be greater than or equal to 0 for all possible values of it. So let's kind of look at this. If you look at this graph, you note that the y-axis is sitting there at 1 over 60, right? That's a uniform distribution, okay? Because all of the things that we're looking at are uniform. They all have the same probabilities. And if you look at the x-axis, you're starting at 0, and it goes all the way out to 60, right? So it's inclusive of every opportunity we have, okay? So any questions on that? So if you ever, they say, what does a uniform density function, what does a uniform density population look like? Then it's going to look like a bar, right? Just like a big old rectangle. Yeah. Standard deviation. Yeah. And we'll get to that later on because we'll pull it in on some things. So, yeah. All right. So, any questions about what the graph of a uniform density function looks like? Y'all good? All right. All of this is kind of leading us into a uniform distribution, basically the bell-shaped curve. So relative frequency histograms are symmetric and bell-shaped are said to have the shape of a normal curve, right? So when we're looking at this, what we talk about bell-shaped, and if you think about the old bells, they're kind of up and they're symmetrical about the midline, right? So that's what we're looking at. They have a host of properties and stuff and things that go along with it. So a continuous random variable is normally distributed or has normal probability distribution if its relative frequency histogram of the random variable has the shape of a normal curve. So you say, what's the shape of a normal curve? Well, it's a bell-shaped or symmetrical curve, and that's what it looks like. So you'll have the mean, which is right smack dab in the middle, right? You've got the mean, which is right here. Here's the mean, and then you've got inflection points. Now this is 1 plus the standard deviation, right? So that's the standard deviation. That, okay? And you can have, so this will be the first standard deviation. You can have second one and third one, right? So, and of course you can have standard deviations below the mean. Okay, so just kind of, when they talk about inflection points, they'll use that vocabulary, inflection points. They're talking about 1 standard deviation, 2 or 3, above or below. They're looking at a perfect standard deviation above or below the mean. Okay, questions? All right, so some properties of a normal density curve. It's symmetrical about the mean. Because it's bell-shaped, the mean, the median, and the mode are all equal, right? If you think about all the properties that we learned when we're looking at skewed left and skewed right, think about that in terms of median and mean. So the inflection points are mean plus 1 standard deviation, or mean plus the standard deviations, or the mean minus the standard deviation. The area under the curve is equal to 1, right? So we still have that 0 to 1 because it's a probability, right? Or a proportion, right? It's the likelihood of that happening, okay? The area under the curve of the right equals the area under the curve of the left, which is equal to 1/2. And if you think about, you've got this, you've got 50% on this side, and you have 50% on that side of the mean, okay? Your mean is smack dab in the middle. As x increases outbound, it gets larger and larger. The graph approaches but never reaches the horizontal axis. As x decreases bound, gets more and more negative. We say decreases bound, heads towards negative infinity. The graph approaches but never reaches the horizontal axis. Now, you have what's called the empirical rule. Okay, and the empirical rule is basically a dissection of the bell curve, and it lets you know how much per each standard deviation, how much of your data is contained within that. Okay, so we say approximately 68% of the area under the normal curve is between +1 and -1 standard deviation from the mean. 95% of the area is between +2 and -2 standard deviations from the mean, and then 99.7% of the area is between +3 and -3 standard deviations from the mean. Now, what the heck does that mean? So here you go. So there's no better way to describe that other than what you're seeing, right? So you need to make sure you understand the 68, the 95, the 99.7, right? This little diagram that also breaks it down within inflection points and above the mean and below the mean as far as percentages is really good when you're looking at having to figure out how much, what's your probability of something happening per an X value, okay? And you normally look at this wherever you're at. The curve is normally shaded, or the area that is spoken or referenced to is normally the area to the left of whatever you're looking at, right? Now, you may get into some of the things where they talk about what is the area to the right of that, in which we would do the complement, right? 1 minus the area to the left to get what's the area to the right. And we'll do that. We'll look at some things that take that into account. All right. All right. Interpreting the area under a normal curve. So if we say the weights of giraffes are approximately normally distributed with a mean of 2,200 pounds and a standard deviation of 200. Well, what the heck does that really mean? So, and this is really about as rough. So just kind of bear with me when I say that this is symmetrical, okay? It's a rough sketch. So this is the mean. So the mean is 2,200, right? And we should have, if standard deviation, 1 standard deviation to the right, well, that would be what? 2,200 plus 200, right? Which would be 2,400. And if we go another standard deviation from there, we're looking at 2,600. And then, of course, a third deviation, standard deviation from the second one would be 2,800. Okay. Now, again, if we go above it, we can also go below it. Okay. And of course, these are rough sketched. Okay. These ought to be vertical lines. So 2,200 pounds minus 200 gives me 2,000. That's one below it. 1,800. And of course, 1,600. Okay. So just kind of dissecting this, you need to be able to, one, draw a normal bell curve, right? And be able to put the mean and standard deviations, right? So 99.7% of all the giraffes weigh between 1,600 pounds and 2,800 pounds, right? Because 99.7% of our population is within -3 standard deviations all the way up to +3, right? So if we look at 2,000 to 2,400 pounds, then 68% of our giraffes would weigh between that, right? Does that make sense? So just kind of looking at that. So we're looking at a particular one, and we're looking at, it says 2,100. So we're kind of looking at right here, right? We'll go right here and we'll say, okay, that's 2,100. And so we're going to shade everything to the left of that, right? Shade the area under the curve to the left of 2,100, okay? Now, you notice that 2,100 does not fall on a perfect standard deviation. But they tell us that, okay, after we shade it, they say, suppose that the area under the curve to the left of x is 30 point or 0.3085, right? They say that all of this right here is 0.3085. Well, what that means is 30.85% of giraffes weigh 2,100 pounds. Or the probability of a giraffe weighing 2,100 pounds is 30.85%, right? Okay, so that's what you're looking at. Now, I've got this one over here, and it kind of shows, it's kind of, it's technology graphed and all that, and it shows. But the big thing I want to leave you with is this. You can talk about the area under the curve, this 30.8 or 30.85% or 0.3085 as being a proportion or a probability. Okay? So you've got to understand that it's a proportion because it's a ratio, right? If it's 0 to 1, it's a ratio. It's out of that, right? So that's what a proportion is. So the proportion of drafts whose weight is less than 2,100 pounds is 0.3085, and then the probability that a randomly selected draft weighs less than 2,100 pounds is 30.85, right? So those things are synonymous. So that's what the big key takeaways is area under the curve. What does it mean? It's a proportion and a probability, right? How much is in the inflection points of 1, 2, and 3 standard deviations above, and then 1, 2, and 3 standard deviations below, right? The 68, the 95, the 99.7s, right? All right. So any questions about that? Again, it's just laying down the fundamental frameworks of the empirical rule of a bell-shaped curve and kind of getting you acclimated to different vocabulary and so forth. Now, here's some of your stuff in the homework. And it says the graph of a normal curve is given on the right. Well, it's given below. I grabbed both of them. It says use the graph to identify the mean and the standard deviation, right? So this little symbol right here means mean. And then this little symbol right here, right, means standard deviation. Okay? So I'm going to give you, I don't know, we'll give about 45 seconds to kind of look at that and kind of decipher what you think the mean is and the standard deviation of those. And then we'll come back and we'll look at it. Okay, so do both of them. Okay, so let's look at the first one. This is the mean. So the mean is what? Negative 17, right? And it has a standard deviation of what? 5. Well, it's just 5. Because you're going to go above and what? Below it, right? So if I were to add negative 5 to negative 17, I'd be at negative 22, right? So just kind of think of standard deviation. We've already talked about it being unitless, right? So should be positive there. All right, now this one, here's the mean. So the mean is 2. What's the standard deviation? 15, right? So this is plus 15, this is plus 15, and this is plus 15, right? And on this side, it is minus 15, right? To get to these points. Okay? Any questions about that? All right. Now, they got a couple more questions besides this one. There's like 2 more problems in the homework, 2 or 3 more problems that have to deal with, I guess, more theoretical type content type, understanding type problems. But I didn't want to put those on there because I wanted you to think about them before you answered it. Because if you answer it true, and it comes back false, then you know it'll pop up and it'll tell you what you needed to know in order to kind of answer that. Okay, so here's one. Suppose the lengths of human pregnancies are normally distributed to 266 days with a mean of 266 days and a standard deviation of 16, right? Completes A through B. So A kind of is 2 parts, okay? And they're looking at 230. If you look at this, if you make the graph go up, if you blow it up, they're talking about, they're talking about the area to the left of that, right? So, and I want to draw your attention to this. Do you see these keywords that I just underlined right here? proportion and what? Probability. So they're going to ask you one time with the word proportion, then they'll ask you again another right after it with the word probability. I want you to understand that those are the same, right? But this is less than 230 days, and it tells you that, okay, figure A represents the curve, normal curve with a mean of 266 and a standard deviation 16, with the area to the left of 230 is 0.0122, right? So basically what that is saying is, if you look at that, the area below it is saying that 230 days, you have a probability of 1.22% of that happening, right, at 230 days. So I'm not sure what that equates to in months because I don't have my calculator, but it's less than 8, right? It's about 7.5 months, somewhere around in there, because 240 would be 8 if you consider 30, right? So, so the 1 point in that, this is 0.0122, and if we look at this, this is really 1.22%, right? It's a probability, right? Proportion. So you have a 1.22% of going or having your child in the 7th, and that's pretty low, right? Unless there's complications that make that arise. But on a normally distributed curve, that's what you got. So basically, you can sit here and look. They ask you the same thing. It's less than 230 with this being the area underneath. Then they say, they just kind of flip it. You got to do it for one same proportion, one doing it for probability. And then they look at part B, and they're saying, okay, the right is the normal curve with 266 days with 16 as standard deviation. What's the area between 235 and 285? So it's right in here. So they tell you that that area is 0.8561, which is really 85.61%, right? Okay. So you have an 85.61% of going into labor, right? Between 235 to 285 days. Right? So, and it does the proportion and it does the what, guys? Right. It'll turn around and do the probabilities too, right? But you're looking at between, right? Not less than or more than. If they're less than or more than, they're talking about this area right here, and then they're talking about this area. So they're just kind of, can you understand how it's graphed, the verbiage, right? Any questions on that? Anybody? Pretty good? Okay. Well, that's all for 7.1. There's a couple more, but they're pretty easy. Really, really content type questions, okay? So, any questions out on Zoom on this? The basic questions that they're giving us are interpretations based off a normal curve. Now, all right, if you don't have any questions, we'll turn around and look at 7.2. Now, here's where the fun begins, okay? And I say the fun begins because we're going to turn around and we're going to calculate z-scores, and then we're going to turn around and look at z-scores and look at the area based off a chart. Okay, so we're going to learn how to read it off a chart, and then we'll also learn how to calculate it on the calculator because the calculator can do it for you. All right? All right. So, 7.2, applications of the normal distribution, right? So find and interpret the area under a normal curve, right? We're going to find it and we're going to interpret it. So they're going to give us a z-score, right? Because if it doesn't land on a particular standard deviation, then we can calculate what that z-score should be. Okay? So, and then we'll find the value of a normal random variable. and we'll look at it based off percentiles and then also area. So we'll work it all the way through, and then the other type is working it from the area or percentile back. So we will have come full circle on this. All right, so here's the z-score, right? I said, okay, you're going to have to calculate a z-score. Well, in order to calculate a z-score, it's your x value minus your mean divided by who? Standard deviation. There you go. Right? So suppose that the random variable x is normally distributed with a mean and a standard deviation, right? Then the random variable is normally distributed with a mean of 0 and a standard deviation of 1. Now, we'll talk about that because we're going to use those values when it comes to looking at some things in the calculator. Okay? So we don't have to know what the mean is in the standard deviation when we're given either the z-score or the area underneath it. We can work back, right? Because we can assume that the mean is 0 and the standard deviation is 1, right? For a normally distributed curve, right? So the random variable z is said to have the standard normal distribution right there. Z is x minus mean over the standard deviation. Any questions about that? So, let's, I needed that. All right, so let's kind of look at this. The table gives the area under the standard normal curve for values to the left of a specified z-score as shown in the figure, okay? So when you look at, when it has a little box on your problem and it says table, what they're going to do is they're going to give you a z-score table. And you can pull it up, you can look at it, okay? So you've got that on the problems, as well as when you take the test, you'll have that if it is needed, right? There'll be a little thing, be like that, right? Something to that effect. All right, so what they're giving you is that z-score. Now, let's look at this. IQ scores can be modeled by a normal distribution with a mean of 100 and a standard deviation of 15. And individuals whose IQ score is 120 is 1.33 standard deviations above the mean. All right? 1.33 standard deviations. That's the Z value. That's your how far it is above the mean or how far below it, right? So you've got to kind of think about like this. If the Z score is positive, then it is above the mean. Okay? If a Z score is negative, then it's going to be below the mean. Okay, so z-scores can be positive or negative, and it will tell you where it's located or what side of the mean it's going to be located on. Okay? Any questions about that? Strictly a chug and plug, right? Got to have the mean, got to have standard deviation, got to have an x value, right? So, if we go the area under a standard normal curve to the left of z equals 1.33. Now, when you read a z-score or a z-table, you're looking at, you come over here, you go 1.3, right? So you'll read the tenths place on the left-hand side, and then your hundredths place will go horizontally, all right? So it's always 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 1.30, 1.31, 1.32, and you look and see right there, 0.9082. Okay? So if you think about it, that is 90.82%, right? Where that's located on that bell curve, that's over to the right, right? It should be above 2 standard deviations, right? In between 2 and 3, somewhere around in there. And I have to do the math. So it may be, I don't think it's above 3. I think it's in between 2 and 3, but don't hold it. Hold me on that. But anyway, it's on the right-hand side above the mean, right? And what they're giving you at 0.9082 is the area underneath, the proportion or the probability that that particular thing will happen, right? For a normally distributed curve. So really these problems that we're walking through are really getting you to look at how to read it. Okay, we had a positive z-score, so you'll have positives and you also have negatives. The tenths are over on the vertical, right? And the hundredths place is horizontal. And then where they intersect, that's the area underneath that curve. Any questions on that? All right. So let's look at this one. Well, they graphed it, right? So we're also going to look at it when I talked about this. You know, how do you find the complement? How do you find, because they may say, you know, they may give you percentiles, right? They may turn around and want the area above that. What's the probability that it won't happen, right? As compared to it will, so forth, right? Or the area below it may be the probability that it won't happen. And then the complement would be the probability that it would. So what you're doing is to find the complement, the other side of where you're looking at, the rest of the area is just 1 minus that, right? So if you look at that, you get 0.0918, which is really 9.18%, right? 9.18% is right here. All that right in there, right? And we found that by doing 1 minus, because the area that they're giving us, the probability that they're giving us for a z-score is always to the left. It's always the area of everything shaded to the left, okay? Any questions on that? Y'all good? Yeah? All right. Ooh, got some more people that joined. Let's see. All right. So now we talked about 34%, 68, right? And then the 13.5 and 13.5 and all this, how the empirical rule, how it split it up, right? With the percentages where it said 68. So what they've done is they have only went back and said, okay, look, here's the area underneath this 0.3413, 0.3413. How do you think they got 68%? How do you think they got 95%? Okay, so they, you know, how much is between 1 and 2? Well, 13.5%, right? Okay, -1 and -2, same. This symmetry. So just kind of, where did this empirical rule come from? It has to deal with the area underneath the curves, those percentages, okay? And those come from a Z table. All right, any questions on that? Kind of putting together the pieces of the puzzle a little bit, filling in, yeah? If we hit anything that you go, I don't know. No, not yet. Pretty straightforward. Yeah. All right. So let's look at this one. Here's just an example. I wanted to give this. This is a z-score of -0.38, right? Because it's negative, we know it's located where? Huh? To the right of the mean? Oh, no. To the left of the mean, below it, right? Okay. So if it's negative, it's going to be below the mean. So, and we're going to go, so we need negative 0.3, and then the hundredths place is the 8. So that's going to be 0.352, right? Which is 35.2% probability that whatever that's talking about, whatever that z-score is relative to, of happening, or, you know. All right. So we've done a positive, we've done a negative, we've even looked at ones that are kind of in between. Let's look at this. Well, this is a complement, right? So area under the curve to the right, and it's called Z naught, 1 minus the area to the left of Z naught, right? Well, I guess there is a particular word for that, and it's not Z naught. Let's see if I can think about it. It's in here. Ba-da-da-da. Sub alpha, right? Sub alpha is what it's going to be. Z sub alpha is what it's called, the area to the right. So if we're looking at this, find the area under standard normal curve with a z-score of 1.25. One, we know that that encompasses some area to the right of the mean, right? All the way down to the left, right? So if you kind of look at it, it's kind of looking like this, right? Maybe somewhere over here, kind of all the way through, with this being the mean. So we're looking at all of this. And if they want the right-hand side, then they're looking at the blue, right? But the table is only going to give us the green. All right, this table, this 1.25, this 8.899 or 0.8944, that is the green. That is everything to the left of the red line, right? But we're wanting the blue. Well, we're going to use the complement, right? 1 minus that gives me 0.1056, which would be 10.5%, right? Any questions on that? So we got the area below. We've looked at the area above, how to find it. And then we'll look at find the area between these, right? Well, a z-score negative 1.02 happens to be below the mean, and a z-score 2.94 is going to be somewhere above the mean, right? And if you look at that, we'll put this right here as the mean. We're going to say, okay, this is a z-score of negative 1.02, right? And this is going to be a z-score of 2.94. So what we're looking at is everything, let's go blue, everything right in here. All right, so you find the z-score for 2.94, and that's 0.9984, and then you'll find the area or the z-score for negative 1.02, which is 0.1539. It's the biggest one minus the what? Smallest one, right? And that 0.159 happens to be all of this, right? So you've got the to the left of it, and then you got from 0.294 all the way to the left, right? So this is kind of, see if we can draw this. This is from here to there, and then this is from here to here. So if we subtract these, then we're left with what's in here, right? Which is 0.8445, which is 84.45% probability. So you're subtracting out the little bit of area, the right there at the tail on the left to get what you want in the blue. Okay. Any questions off of that? Is everybody good? All right. So procedures for finding the value of a normal random variable. Okay. So we're going to draw a normal curve and shade the area corresponding to the proportion, the probability, or the percentile. Now, they threw in another word, did they not? Percentile. That's the same as the probability or the proportion. Okay. That's the area underneath the curve. So it can be called one of three things. Now, use the table V to find the z-score that corresponds to the shaded area. You're going to have on the problems, you're going to, if it's referenced in the z-score, you're going to have that table so you can pop it up, right? So really, what does that really look like? So here's a z-score table. And I could put this up in, I can put it up in Blackboard if you want to copy it off, but it goes to 5 decimal places, okay? Some of them only go to 4, but this goes to 5. And you can see that it's -3.9, that'd be O, -391, right? -392, right? This is the hundredths place, and the going across is the, going vertically is the tenths, going across horizontally is the hundredths place. And so you've got all the way down to 0, right? Or I hate to say -0, but and then it goes positive. And as it goes positive, look at your area of your numbers, right? Well, at 0, 0, it's at 50%, correct? And you would expect as the area goes right that the probability goes up accordingly. And it does. And you can see it all the way to here, 0.99997, right? Right, 3.99. Okay. So I'll put this up there. You can kind of use it, but it's the area to the left. So you can obtain a normal value from this formula. X equals the mean plus Z standard deviation. Right, so here's another formula. When they talk about normal value, they're talking about like the 2100, okay, of the weight for the draft. That's an X, right? The z-score was like, I don't know, negative something, right? And the standard deviation. So if you were to take the mean plus the standard deviation or the z-score times it, you would come back out with the actual value that would mean something, some X value on the graph, right? All right. So let's look at this. Combined verbal and quantitative reasoning or score on the GRE is normally distributed with a mean of 1049 and a standard deviation of 189. What is the score of a student whose percentile rank is at 85th, who is at the 85th percentile? Okay, so we're trying to find, okay, what did they score if they were ranked 85th with a mean of 1,049 and a standard deviation of 189? Well, this 85 percentile is the score such that the area on the normal curve to the left is 0.85. Okay, well, if we go look at the area. That's the area, right? So if we look here at the 0.85, that's at what? Let's see. 0.85 is, you go, well, it's not exactly. You're right. Right there, right? So 1.04, right? Y'all see that? 0.85083? That's 0.84849 and 0.85. So that's the closest one to it, right? Now you can split between these, but you don't have to. So 0.85083, 1.04, right? Going out and coming down. Well, we found that and then we went up, right? And over. So that's where that came from. The 1.04, okay? They told us that they were in the 85 percentile. That's the area underneath the curve. So we went and found a z-score that equated to that, right? 1.04 times 189 plus 1,049 gives me a score of 1,246, okay? A person who scores 1,246 on the GRE would rank 85th in the 85th percentile, okay? So they're giving you an X value and asking you to go find, but that the z-score are going to give, well, I hate to say they give you an X value. They want you to find an X value, right? What is the point on that graph of that horizontal axis? What is its numerical value? Given that, you've either got the area or a percentile, which is really equivalent to an area, right? So you just know that if they give you an area or a percentile, they're talking about that's the area underneath the curve. You need to go find a z-score for that, right? Okay. All right. Now, you can do that by hand, and we'll also look at that in doing it on the calculator. All right. Questions? So good. I put up 3 videos that deal with finding the z-score on the calculator, which is really based on 7.2. 7.1 is just more theoretical, foundational concepts of the normal distribution. Notation Z alpha is pronounced Z sub alpha because it's a subscript, right? Z sub alpha, and that is talking about the area to the right. It's the z-score such that the area under the normal curve is to the right. So Z sub alpha. That's the correct terminology for that. Any questions? All right. Now, let's go have some fun. Because really that's all of the content right there for 7.2. Let's go see how we're going to apply it when it comes to homework problems. Okay. So the first homework problem that they have is say, okay, go determine the area under the standard normal curve that lies to the left of z equals 0.47, right? All right, so here we go. 0.47. We know it's above what? The mean, okay? So if we go, and this right here problem will have a little Z table icon, right? So you can go to that, but I'm going to use this to kind of let you kind of see. So erase all that. We need to go to 0.47. So we're going to be right here, positive 0.4, right? And then we're going to go right here at 7. That's going to give us what? 0.68082, right? 0.68082. So 68%, right? Okay? That's what that equates to. Now, any questions about how we read that off of the Z table? They gave us the z-score. We had to go find the area underneath the curve, and that's the area underneath the curve to the left. Okay? And it says they want the area underneath to the left. So that is going to be 0.68082. All right? Now, you ready? Let's do another one, and now I'll show you how to do it on the calculator. Because you can do it on the calculator as well, but you have to understand some of the things that you're typing in. Okay, so the next one is a negative 1.62, right? Z equals negative 1.62. So we're going to go right here. We're going to go, well, we know it's below. It's got to be below the mean because it's negative, right? So just understanding that is going to help us. Negative 1.6. So we're going to make this go here. And let's just do this. All right, so we're at negative 1.6, right? This is 0. This is 1, 2, 3, 4, right? 4, 5, 6, 7, 8, 9. That's the hundredths place, right? So 0, 1, 2. All right, so we need negative 1.62. We need this value right here, right? 0.05262. Do y'all agree? Because you can't see my 0.00, 0.01. You got to know that 0, 1, 2, 3, 4, 5, right? And it's the hundredths place. So, and when we do this, this is going to equate to, okay, well, all we're going to do is take it back over here, 0.05262, right? Well, if it's to the left of the curve, we would not expect any area underneath the curve that is to the left of the mean to be above 50%. Because the mean is in the middle, and that's at 50%. So all the area to the left of the mean has to be below 50, right? Okay, to 0.5. Now, let's talk about how do we do this. How do we do this on a calculator? All right, so we're going to do these last two, okay? And we can do that one there, but it's not going to really matter. So we will Z equals 0.49. Now, how do we do this? So we're going to do this. We're going to use what's called the normal CDF, normal cumulative distribution function, right? Now, we're going to use this to find a z-score, all right? We're going to use this function on our calculator to find a z-score. So you kind of go, if I were you, I'd be taking a sheet going, okay, kind of like a tabular form. If I need to find this, this is where I need to go as far as a function. And here's some examples of how it's written in, because that's going to be very handy when it gets to your final exam, right? So we've got, and you look at this, it's going to give, I'm going to put this in, and then we'll do it, okay? And then this is going to be 0, and this is going to be 1, okay? Now, this is going to be the mean, and this one right here is representing the standard deviation, right? We said a normal distribution curve with a z-score is with a mean of 0 and a standard deviation of what? 1, right? So we're going to use that in order to find it, right? Because it told us we could. Now, where does the negative 1e to the 999? Well, that's scientific notation. That's negative 1, right? E, 999, that's 99 decimal places to the left, right? That's negative infinity. It's as much as you can make it. So let's kind of look at it. So if you get your calculator, we're going to go second bars, right? And we're going down to number 2, right? Number 2, which is normal cumulative distribution function. So we're going to hit number 2. Now, it preloads if you have a 84 TI-84 that has the latest software, and I say the latest software, it could be as old as 5-6 years ago, and it still be able to do this, right? It's going to come with this menu type format, and it's got the lower being negative 1e to the 99. Now, if you don't have that and you need to type it in, then you hit the negative, which is to the left of enter, right? You see that little negative down there? 1, and then you go second comma, all right? Second comma, because you see that EE? That EE will give you that scientific notation to E. Second comma is the keystroke if you have to type this in, right? Now, we said, okay, if I hit enter, with the lower bound should preload for you. But if it doesn't, you've got it. Now, how far up the area are we given, right? It's telling us, well, it's giving us a z-score, right? What did I put on it? Did I just do that wrong? Hold up. No, it's not define a z-score. Let me erase that. Define an area given z-score. Okay, so there. To find the area given a z-score, this is what you're going to do. Because I've got, and I'd call it right there, I put it negative 1e to 99 comma z-score comma 0 comma 1, right? We got to put the z-score in. Okay, so let's go back and let's go over here into our calculator. All right, so the z-score that we're going to use is 0.49, right? Okay, now the mean we said was 0, and the standard deviation is going to be what? 1, because we can do that finding using z-scores, right? And then you're going to come down and hit paste. Now, this paste is going to be what it looks like if you didn't have the menu format, the old operating system for TI. We had to hand punch everything in with commas, right? So if you kind of look at that, you should see that negative 1e99 as your lower bound, all the way up to 0.49, comma, with a mean of 0 and a standard deviation of 1. Y'all ready? If you hit enter, you get 0.6879. Now, I'm at 4 decimal places, right? If I want more than that, then I need to just go to mode, and instead of being on 4, I need to go to 5 or 6, right? Whatever it tells me I need to. But it gave me 0.6879, right? So, it's going to go back over here. 6879, right? Of 0.49. Y'all agree? Yeah? All right. So, let's go look at it, see how it equates to the z-score table. 0.49. So we know we got to be on positives, right? So we're going to go here. 0.49 is 0.6879 what? 3. And if you go to 4 decimal places, it'd be 0.6879, right? Does that make sense? So it correlates. Now the table, my table that I'm using goes to 5. The table that is in Pearson may only go to 4. Okay, so you need to look at it from a homework standpoint and say, what does it require me to go to? And it'll tell you. It'll tell you. All right, so you want to do another one? We got another one, right? Let's do it on the calculator. You ready? So we're finding a 0.56, right? A z-score of 0.56. Well, we're doing a normal CDF. It's going to be negative 1 e to the 99. That'd be 0.56, comma 0, comma what? 1, right? If you can write that out, then it'll make a little bit more sense. You'll be a little bit more comfortable putting it into your calculator. Y'all ready? So we'll clear this out so you can see my steps. Second, vars, number 2. And, of course, the lower bound is all the way negative infinity. We have what? A z-score is 0.56. Mean of 0, standard deviation of 1, right? Now, it may come up as being mean blank, standard deviation blank, right? But you need to use 0 and 1. Now, because they didn't give us any of it, did it? So we can use that. Paste it, and then hit enter. Ladies and gentlemen, 0.7123. That is your area underneath the curve to the left of that particular z-score. Fair enough? All right. Now let's go look at another problem. Well, before I leave that, any questions on this? All right, you see how I put this to find an area given a z-score? Here's the stuff, what things are, right? And then an example. You need to have an example and what it equals to so you can quickly do it in your calculator and make sure, okay, that you typed in and know that it came out to be correctly or correct, right? That you correctly got the answer that is given, right? So just kind of know that. I would make a table if I were you. All right, assume that random variable x is normally distributed. It's a bell-shaped curve, right? That's what it tells us. With a mean of 50 and a standard deviation of 7. Well, they gave us the mean and standard deviation, right? So compute the probability to be, and be sure to draw a normal curve with its area corresponding to the probability shaded, right? So probability of x is greater than 38. X is greater than 38. So looking at our bell curves, we have 38 with the area below it, right? We have 38 up to 50, 50 being mean, so the area between that. And then we have over here 38, and then everything shaded to the right. Well, where is it? Is it A, B, or C that is correlates to the area to the right? C, right? Now, we've got to find the probability given an x value, right? Okay, given an x value. So if we were to look at this, we're given x equals, if we look at this, mean plus z standard deviation, right? Correct? So if we were to sit here and we go, okay, well, we got to plug it in. That's going to be a 38. That's going to be 50 plus the z times 7, right? And then we'll, of course, minus 50. And that gives us what? Negative 12 equals 7z. And we get a z score of negative 1.714. Okay? So that's how you find a z-score of negative 1.714. And from that z-score is going to reference this unshaded portion right here. Okay? Everything to the left of that. Does that make sense? No. Yep. We're given a variable, an x, we're given the mean and the standard deviation. We can first find a z-score, right? That z-score is going to give us the area from 38 down, right? From here down. That's what that z-score is going to give us, right? Now, we got to go to the z-score table and look at basically negative 1.71, right? And figure out what that area is. And that area, if you do that, that area is going to come out to be the area. It's going to come out to be 0.04363, right? If you go look at your z-score table, negative 7.14, negative, right? 1.7. It's right here, negative 1.7. That's 0, 1, right there, right? You'll see where I got the value. You go, well, Palmer, it's 4 thousandths more, right? Okay, it'll be okay. You're getting to the hundredths, right? Okay, so that's 0.04363. That's what it's saying is the area to the left of that. Y'all with me? So that's where I came up with. I want to hit X there. That's where I came up with this. Now, I want the area, the question said the area to the right of it, right? Greater than 38, right? So we'd go 1 minus 0.04363, which would give us 0.9563. That's your answer. We used the complement, right? We had the area to the left, but we really needed all the area to the right. So 1 minus that. Whoa, whoa. Oh. How'd you get 0.0433? Read it off the table? Oh, you put it in there. We'll do it. Yeah, we'll do it. Reading it from the table and then doing that, we'll find, right? All right. Okay, so how can we do this on the calculator? We can do a normal CDF, right? And so we can do a normal CDF. It'll be -1e to the 99, right? Comma. Well, the next number should be what? What did you get when you did 38? And a mean of 7. Yeah. All right. So there's 2 ways, right? So you can use the x value, right? Right. Now, you can use 0 and 1, or you can use 50 and what? 7. It's still going to come out to be the same thing, right? Now, the x value happens to be what? 38. Okay, so let's go type it in so we figure out what we've got. Now, what that's going to give you is the area to the left of that, right? So, and I'm at 4, so let me clear this out. Clear, and then let me hit clear here. So I'm going to go second bars, number 2, right? Lowers that. Upper, we're going to put what? 38. And then we can use 0 and 1 and a paste, right? We'll just go ahead and put it as 0 and 1 and paste. Then we'll turn around and do it with 50 and 7. Should be the same thing, right? Should be. Boom. Did I? Oh, hold up. Not for that. Sorry. If you're using, if you're using the 38, it has to be the mean and standard deviation that goes along with that 38. If I use the z-score there, then I could put 0 and 1. Okay. So let me go back. Let me go second bars 2. So we'll go 38. Then we have a mean of 50 and a standard deviation of what? 7. So when do we use 0 and 1? With the z-score for the upper, right? Does that make sense? And if you paste that, you get 0.432, right? Okay, now mine is rounding to 4 decimal places. The table went to 5, right? Okay, so that's to the area to the left, but I need the area to the what? To the right. So I can very quickly go 1 minus, and if I go second negative, that gives me this answer, and I can hit it and be 0.95 what? 68, right? So that's out in the thousands. So it'd be within tolerance, right? Because I got 0.9563 with that. So the calculator is going to be a little bit precise because we were needing a z-score of 1.714, right? So we were 4 thousandths off. So that's the error that's introduced there. Okay. So any questions about that one? All right. If you use an X value, you got to use its mean and standard deviation, right? If you use a z-score, you can do what? 0 and what? 1, right? You really only have to care about the mean, right? All right. Any questions about how we did this? Pretty straightforward. It is until you put a little bit of time between it and kind of go, what did I do where, so make sure you're taking really, really good notes on what to use and where to use it, right? What do you need to find and what options you have? That's the biggest thing that I want to leave with you on this. Now, all right, so this is the last problem. So we're assuming a random X value with a mean of 50 and a standard deviation of 7. We're given the 78th percentile. Okay, what we're given is an area. Okay, we're given the area. We need to find what? What the X is, right? We need to find out what the X is, right? We need to find the X, right? We're given the area. Y'all agree? Now, you can do this by hand. Sure can. This 0.78 happens to be the area. So if I went and looked at the table over here, if I go to the table and I go, okay, I need an area to be 0.78 or pretty daggum close, right? So I would do, that's 0.7823, right? And that's 0.7935. Which one's closest to 0.78? Which one? This is 230 above it. This would be only what? 65 below it, right? This value is a little bit closer to the 0.78, right? That's the area underneath. Well, what does it correlate from a z-score? 0.77, right? Does that make sense? We're here. We're at 0.77, right? So if we were to go back over here and we would go, okay, now X is equal to the mean plus the z-score times standard deviation, right? Y'all agree? So we know that the mean is 50. We know that the z-score happens to be what? We just found it. .77, right? Don't get that confused with it going, oh, that's the point. It came from there. No, we looked at, this is the area underneath, right? This is the area underneath. This happened to correlate with the table, right? You with me? Now, times 7. If we do this, we get, ladies and gentlemen, 50 plus 5.39, which is 55 point what? 39, correct? Yeah? So that's how you do it by hand. Would you like to see how you do it with a calculator? Okay. Now, again, we're given what? Area. And we need to find what? An X. So we need to go to an inverse norm. Okay. So when we do this, we're going to inverse norm. The first one's going to be the area. The second one's going to be the mean. And the third one's going to be the standard deviation. So this right here is area. This happens to be mean. And then this right here is, guess what? Boy, I put that on the wrong thing. There you go. Good. That's the standard deviation. Now, you ready? And I think it's inverse norm PDF. Okay, so we go over here to our calculator. I'm going to clear some things out real quick. Right, hit the clear screen. So second bars, all these distribution things, and we're going to go to second bars. Look at number 3. Oh, it's just inverse norm, right? Yeah, it's just inverse norm. So it ain't inverse norm PDF. I don't know why I wrote that down. So it's inverse norm. So we're going to go to number 3, right? Now the area. Now, this right here is asking tell. Yeah. All right. My other calculator didn't have that as well. So we'll just see. No, it doesn't have to show the tail. No. It's an updated, it's an emulator type software. So we're going to put 0.78, right? Yeah. The mean is what? 50. And the standard deviation is what? 7. All right. I'll have to look and see what, yours ain't going to come up with that, so don't worry about it. Yours did? I don't know. I'm gonna try it both ways. It could be talking about skewness, right? Could. So I'm gonna leave it left and see what it comes out to be, and then no, it came out to 55.405. It came out to what it's supposed to be. Okay. It's either talking about skewness or the area, left, middle, or to the right, maybe. I don't know. Let's see. So it gives you a lower and an upper bound for center. Aha. And if it's right, then hey, all right, that's pretty cool. But it doesn't matter. Just use left. Just use left and you'll be okay. Because what you're dealing with is area to the left. Fair enough? Okay. So if you get this, maybe yours does, maybe yours doesn't, when you go to number 3, it's talking about the tail is talking about the area. Just keep it on left. And if you need it to the right, then it's 1 minus that, right? There. All right. So could I find a z-score? Could I find a z-score from this? Yes. And if I wanted to find a z-score so that I could do the calculation by hand to kind of look to verify what I did on there was correct, then this was what I would do. Z-score, I'd use a mean of 0, standard deviation of what? 1, right? 0.722, right? We had 0.77, right? By the table. So it would give you the z-score if you use the 0 and 1, right? It'll give you your answer, your x value, if you use the 50 and the 7, the real mean of the problem and the standard deviation. It works both ways, because what if it didn't give you the standard deviation nor the mean? You could still find the z-score, right, and still calculate it by hand, correct? So there. So there, that's it. That's all I got. And it is 6:24 with 52 seconds. So that is done. So 7.1 and 7.2, ladies and gentlemen, that's it. That's a whole lot of computer stuff, or I say computer, calculator stuff on this right here that you better be, how do I write this in? I'd have both of these type examples up there. Does that make sense? What does this mean? What does this answer? What does this mean? And where do I go to get the answer if it's 0.722, right? You know, what do I use that? Well, I'm going to put it back in my calculation, right? I'm going to put it back right here and times it by the standard deviation and go to the mean. But you'd have to have that, right? All right. So that's all for 7.1 and 7.2.